Hello, my name is Scott Cheatham, and I'm with the Richmond Hospital Education Program. And this is a lesson on basic log properties and laws. There's also been a lesson that I've created on introduction to logarithms. So if you're not familiar with logarithms, I would suggest watching and reviewing that first. But if you have some basic exposure in the past to logarithms, then this is an extension that kind of uses the basic logs of logarithms and goes into how we can utilize those to manipulate logarithms. Logarithms is a topic that comes up first in Algebra 2, but really only kind of looking at the graphs of those functions. As you get into trigonometry and then more into calculus, you use logarithms much more. And being able to utilize these laws without using a graphing calculator is going to be important for you, especially as you get into calculus. So while a graphing calculator can solve some of these for you, some of them it cannot. And being able to work on them without a graphing calculator is something that I would suggest you practice during this lesson. So for exponential functions, and then also for logarithmic functions, we do want to review just these basic ideas here, that if we have an exponential function, y equals a to the x, that base, a, is always going to be positive. If you have a negative number raised to an exponent, that ends up flipping the signs and causes issues when you have decimals. And so we're going to treat just the base as always positive, and that goes for logarithms as well. We're not going to ever treat the base as 1. 1 raised to any exponent is 1, and that ends up not having the same properties throughout logarithms, so we're not going to have a base of 1. And then we're just going to assume that we're dealing with all real numbers here. If just reminding, for a logarithm, it is a type of exponent, and the base always is the base. And so whether it's the base of the logarithm or the base raised to an exponent, that number is the same. And for these logs, we're going to, again, assume the base is positive, but not equal to 1. So basic log properties. These are some ideas that we're going to use to build off of. And if we think about this, you can ask yourself, okay, for any logarithm, the base raised to what exponent, that's going to be what these question marks are, equals what we're taking the logarithm of. So for these, if you look at them, I just want you to go ahead and play around with them and see if you can decide what would these answers be. If you need to pause the presentation, that's fine. But go ahead and just kind of on your own, sketch down what you think the answers would be to these 3 problems. So for the first one here, again, you can ask yourself, the base of a raised to what exponent would equal 1? Well, anything to the 0 power is 1. So again, if you're taking the log of 1, no matter the base, that is going to be equal to 0. For number 2 here, you see that the base and what you're taking the log of are the same. And so for that one, that goes to, we would understand here, it's going to equal 1 because the base raised to the first power is going to equal itself. And so anytime where you have the base and what you're taking the log of to be the same value, that's going to always equal 1. And as you see here, this is kind of gets to where if we have an exponent that we're raising in the logarithm, we can see if we think of it as the base raised to our x equals what we're taking the logarithm of, a to the x, that ends up being equivalent. So here, because the base and what we were taking the log of both had a, we can go ahead and say that a to the x equals a to the x. That exponent of x is our answer. So using those ideas and those, go ahead and extrapolate that to these 3 problems. I'm going to pause the presentation and then decide, okay, well, given these with kind of different values in in the logarithms, what would our answers be? So here, for when we evaluate these, we have anytime we have a log of 1, no matter the base, it's going to equal 0. Because again, the base raised to the 0 power is always going to be 1. For number 2, we have the base and what we're taking the log of is the same. And so that's always going to equal 1, because 9 to the first power is 9. And here again, we have the base and what we're taking the log of are the same, but it's being raised to an exponent. All right, our answer is going to be that exponent. Now, just as a reminder, when you see ln, that's the natural log, and that is a logarithm with a base of e. E is an irrational number. It's a constant that gets used in calculus, and where the derivation of e and where that comes from is something that you'll get more into should you ever take a calculus class. It's something that has many real-world applications of how logs get used, even in finance and other fields. And so the natural log is something that you've probably seen on a graphing calculator, but really it's just a logarithm with the base of e. So when you see that, we're going to assume and understand that the base is e. And so for these three, now again, very similar to what we've been doing, but it's a log with a base of e. Go ahead and determine what you think the answers would be for these three. Very similar to what we've been seeing. Anytime you're taking the log of 1, no matter the base, it's going to equal 0. For the second one, anytime the base in which you're taking the log of match, in this case e, it's going to equal 1. And for this last one here, the base and what we're taking the log of match, it's being raised to an exponent, it's going to equal x. So from those properties, we're going to extrapolate certain logarithm laws. And these are laws that you might notice are very similar to some of the exponent laws that you've been learning since middle school. And again, a logarithm is another way of writing an exponent, so it would make sense that there might be some commonalities in there. But for these first two numbers, I want you to take each part separately. And so again, without a calculator, log base 2 of 4 and log base 2 of 8. Go ahead and determine what those two numbers are and what this would be. So again, another way of looking at a log is asking yourself, okay, for the base, what power of 2 would give me 4? Or 2 to what power is 4? Same thing for log base 2 of 8. 2 to what power would be 8? And from both of those, hopefully you were able to do those in your head. Answers 2 and 3. And so when we add those, both of those logarithms, we get 5. Now, look what happens if we multiply the 4 and 8 together. So 4 times 8 is 32. So log base 2 of 32. So again, what power of 2 is 32? And that answer is 5. Very similar to what we had before. And so that is where we're going to get our first log law. So if we have log with a base of b equals two either variables or numbers multiplied by each other, we can separate those logs and add them together. And again, this goes to if we had our exponent properties, if we have a base raised to an exponent, if we have the same base, we can add those two exponents. It'd be like if you had x squared times x to the third is x to the fifth. Again, those same properties we're going to be able to extrapolate into logarithms. And so we can separate these out. Now, a couple things with that. If we have different bases, this is not going to work. So, for instance, in this example here, it would not work to combine them the same way with one of the logs with a base of 3. And that's because 3 to a certain exponent equaling 8 is going to be a completely different value than if the base was 2. The other thing, just to show you the whole idea of adding the two values, if the adding is inside the logarithm, we can't use this property. We can't separate it that same way. Now think back to exponents, your exponent laws, and what happened if we had, like, for instance, x to the 10th over x to the 4th. Well, we would subtract those and we would get 10 minus 4 and be x to the 6th. Well, the same idea happens here when we are dividing two values inside log. We can separate them, and same idea of subtracting. So whereas before I mentioned 10 to the, or x to the 10th over x to the 6th, we would subtract the exponents. Again, a log is an exponent. We can separate it the same way. Now, our third log law here is something raised to an exponent. This is actually something that, again, if we had x squared, a power raised to a power, let's say we had x squared raised to the 4th power, we multiply those exponents. Well, here, if we have an exponent, we can multiply it times the log. And so another way of writing this logarithm is by pulling that a out of front and multiplying it times log. This can go both ways. So if you have a number front, you could raise it up to the exponent, and vice versa. If you have the number in the exponent, you can bring it out front. And again, that's because we multiply our exponents there. And again, here we call, you had that log base a of a raised to the x equaled x. Well, if we pulled that x down, it'd be like having x times 1 or x. It's another way of kind of breaking it down and looking at how these log laws could be used. So for the remainder of this lesson, we're going to look at some examples, and again, will admit that these are some abstract examples with lots of different variables and exponents and radicals. But before we can kind of get into using logarithms, manipulating them in the real world, we need to understand some of the ways that they can be used. If you need to go back and review some of your radical properties, that might be something that you might want to do. But from these, we are going to want to be able to move back and forth into fraction exponents. Again, not using decimals, we're going to use fractions. And so I'm going to give you a hint for these, for this first one. I kind of broke that one up, how you might start to see it. And then for the second one, I also wanted to show you that one of the first things we would do is rewrite that as something rather than the 5th root raised to the 1/5. So I want you to go ahead and pause the presentation and see what are some other ways that you could expand this. If you can simplify something, that's great. But I want you to see how could you expand this given some of the log law properties that we've seen. So for the first one here, again, we have 3 things being multiplied by each other. We have inside the logarithm, we have 3m squared and the cube root of n. And so we can use a log property in order to split that out and to add each of those logs separately. Again, make sure that you're writing the base of 2. You don't want to drop that. You want to make sure you keep that in there moving forward. Now, log base 2 of 3 I've left alone. There's not much we can do there at this point. I did bring down the exponent of the 2 in front, and I rewrote the cube root of n as the 1/3 exponent. And then our last step there would be bringing that 1/3 down in front of the log base 2 to the n. There is nothing more we can do to expand this, and so this would be our final answer. Now I showed as the first step to kind of help you along, we had the natural log here with the 5th root of m over x squared times y squared. This step here, we have the 1/5, and you'll find with these logarithms we're going to use fractional exponents rather than the radicals, just because what we can do with that exponent. We can move that 1/5 out front. Now that 1/5 we're multiplying by the natural log here, it's going to go to everything. So if we start separating this into multiple logs, we want to make sure that that 1/5 is outside some parentheses or some brackets, as we don't want to drop it accidentally. So as I said, we want to keep that 1/5 outside some brackets. We are going to subtract the log of that denominator there. We're going to pull that out and separate it. Now, because we have the natural log of x squared times y to the 3rd, that actually can be separated into 2 different logs. Notice that I did put parentheses around that because we want to be mindful of that minus, and we would want to make sure that we noted that that would go to the entire logarithm that we just split up. Went ahead and brought down those 2 exponents, and you might have done this a different order, and that would be completely fine. I went ahead and just brought down the exponents, then distributed that minus to both of those logs. And our last step, we just distributed the 1/5, and here we have. Now this is multiple steps. I know it seems a little tedious, and you might have done them a little bit differently. If you got to the same final answer, that's fine. But it's going to be helpful to be able to kind of split these out and manipulate these logarithms as we move forward. Now, rewrite as a single log is basically the reverse of what we just did. So rather than expanding fully, this is taking something that's expanding and writing it as one log. And so we're going to use the exact same problems or the same processes and laws in order to go in reverse and rewrite these 2 problems as a single log. So go ahead and pause the presentation, copy them down, and see if you can get them down to 1 log. Be mindful that you're writing your base as if you need to. Number 1 does not have a base, and so we understand that to be log with a base of 10. But go ahead and pause this now and then come back and we'll kind of go through how we would approach each one of these. You might have done this in a slightly different order, and that's okay. But the final end result should be the same. For this first one here, the first thing I did was I took the constant up front and raised that up as an exponent. And that's something that we can do based on the log laws that we've learned. And the next step, we have two logs that we're adding that have the same base, so we can combine that to one log, and it's log of xy to the third power. That's something where you might have flip-flopped those two steps, and you might have combined the two logs and then brought up the 3, but it should get you the same final answer either way you approached it. Now for this one, we had 3 different ones where we were subtracting. And so you've got to be mindful of kind of what that means. There's a couple different ways that you can do this, as I've mentioned, but I always like to, if there is a constant out front, I like to raise that up to an exponent first. And so that's what I did here. The 1/2 and the 5, both of those raised up to be exponents. Now for this next step, I have just really focused on the first 2 logs, and then I'll deal with the log base 3 of p in a minute. You could have done some factoring out of that negative and combining some different things separately, which would be fine. But we have log base 3 of m to the 1/2 over n to the 5th. And again, if we're subtracting another log, that's going to go down in the denominator. And so for this one here, you can see that basically the 2 where we subtracted the logs there in the denominator, the one that was positive ends up in the numerator, and that's what we would expect for these. Now the one last step here is I did rewrite this log, since it had a fractional exponent, as a radical. Depending on what your teacher says and how you're doing it, it might be fine to leave it with a fraction exponent. Sometimes you'll be asked to write things as a radical. It just kind of depends on your teacher and their instructions. But again, this would be going kind of the full reverse. The previous problems we were asked to expand. Now we're asking to rewrite these as a single log. Now, as some extended practice, as to accompany this lesson, there's a log law practice worksheet that I've also worked out the answers. But before you go to that, I did want to just remind you that you can solve these logs both with a TI calculator and with the Desmos calculator. Depending on which TI calculator you have and the software version that you have, it does make it fairly easy to input a base in for the log. You do want to remember that if you don't have that, or if you're using maybe a scientific calculator or like your phone as a calculator, if you see the log button and the natural log button, that's probably all you're going to see on those. And so it defaults to the log. If you don't see the base, it's a base of 10, and the natural log, if you see the natural log, it has a base of e. On the Desmos calculator, it is, if you're using the graphing one, they allow you pretty easily to plug in the base. If you were to go and plug in some of these values, it could help you with some of it. But on the ones where you have variables in the logs, the graphing calculators really can't do all this for you. And so that's why we're going over these log laws. Again, log laws are derived from our understandings of exponents. As we were looking at them in this lesson, pretty much all of the laws that we derived are ones that came from the exponent laws that you've been learning since middle school. And so I would encourage you, if this felt a little overwhelming, or if you weren't as comfortable with it, you may want to go back and review some of just the basic exponent properties or the basic radical properties. It is going to be important that you understand what fractional exponents mean and how that can be written with a radical, because as you get more and more into logs, you might have more complicated fractions than some of the ones that I showed you here. And so that's something where that's going to be important for you as you move forward. For the log law practice worksheet, I would encourage you to look at my work. Again, you might have done it slightly differently, which is completely okay. But if you get stuck or you want to see how some of them were done, you can look at that before you move on. So I wish you well, and I thank you for listening to my presentation. Hope you have a nice day.